Hi, look, this video is covering titration of a weak acid with a strong base. So we're going to be answering several questions, and I do have a time limit as to how long will this video keep taping. So let's get to it. So we have a titration of a weak acid with a strong base. In this case, 50 milliliters of 1 molar HCN, okay, titrated with 0.1 molar of NaOH. Our Ka is 6.2 times 10 to the minus 10. What is the pH of the HCN to begin with? Now, this is coming from a previous chapter, okay? And if you think about it, you know, Ka is equal to the concentration of H plus multiplied by the concentration of Cn minus over the concentration of HCN. Okay, you'd say, where did you get all this from? Well, keep in mind, we're assuming we're putting the HCN in water, okay, and it's breaking up, and it's canceling out, all right? So, for the sake of argument, what we're looking at, if we look at the reaction, HCN, okay, is going back and forth to H plus Cn minus. This is what's going on. Now we can go ahead and use the ice table in there and look at it and say, all right, well, we started out with 0.1 molar, okay, that's our initial. We have 0 and 0 here because nothing has been dissociated with. Then we have a change. Well, that change is going to be a minus x, right? We don't know how much, and here it's going to be plus x plus x. Okay, that's going to be our change. What is lost here will be gained on this side. So when we get our equilibrium, we're going to have 0.1 minus x plus x plus x. So that's what we've got here. This should be a simple review for you guys. Now, for the sake of argument, we're assuming it's a weak acid, doesn't dissociate all that well with water, so we're going to assume x is very tiny, so we can eliminate this. And basically, we're looking at the Ka is equal to x squared over 0.1, okay? And when we look at that, we got the Ka from the beginning of the problem, okay? I have to speed up here, so eliminating the 0.1 by multiplying it by both sides, we got x squared is equal to 6.2 times 10 to the minus 11th, okay? And thus, x is equal to 7.874 times 10 to the minus 6th, okay? Which means that with that, the pH is equal to the negative log of our concentration of our H, right? That is our concentration of H right here. This is our H concentration. Okay? Negative log of this, and we end up getting a pH 5.1. So that's our starting pH to begin with. Okay? I've got to move on here. So now, moving on to the second problem here, we have a titration of a weak acid, strong base, same conditions, but now the question is, what's going to be the pH when the HCN has been titrated with 8 milliliters of NaOH? Now, at this point, the situation's a little bit different because now we've added some base, which means that there is some canceling out of different things. So, how do we go about this? Well, if we look at the reaction here, we're going to have HCN plus OH minus, and that's basically, you know, that's basic. Let me erase this for a second. Okay, and we're going to get Cn minus plus H2O. Well, wait a minute, what happened to the Na? Remember, it's a spectator ion. It's not going to play a role in this. This is what we have. Now, here, for us, we have our initial concentration here of 0.05 liters multiplied, now it's going to do it, multiplied by 0.1 molar, okay? I have to abbreviate that. So that's going to get us 0.05 moles, okay? That's what we're going to have here for the HCl. That's how many moles of the stuff do we have. Now, here for the Cn to start out with, we have 0. Okay, water on the other hand, it's irrelevant. We don't have to worry about it because it's neutral. Okay, but they did say they titrated with 8 milliliters of NaOH, and they gave us the concentration, 0.1 molar. Okay, so let's go ahead and let's put that in there. So that's going to be 0.08 liters times 0.1 molar, and that's going to get us 0.0008 moles. So that's how many moles of OH that we're going to get. Now, the key thing you need to understand when you're looking at something like this is that this is going to cancel out some of this. It's going to eliminate some of this. Why? Because they're the opposites of each other. And as Paul Abdul said, opposites attract. Okay? So that means how much of this acid is going to be left over? Well, it's going to be 0.005 minus 0.0008. Okay? Remember, this is moles of H plus. Here it's moles of OH minus, and that's going to leave us with 0.0042 moles of H plus that has not been reacted with the base. So there is a remnant that's there. Okay? Now, we've got the moles, okay, but we also know that now that we have that, we also know that the OH is going to cancel out. The OH is also, it's going to be eliminated, so we know that. Now what we need to do is, because it's a weak acid and it's not a strong acid, we have to go and work with the ice table on this. But we've got some information. We have the number of moles now of this H that's left over. But what about the volume? Well, you have to take into account the volume, not just of the original acid, but the 8 milliliters of base that we added in there, because now it's all combined into one thing. So, this is what we have. So I need to, I'm trying to move on, guys. So I'm going to have my ice table. Well, let's see, let's just go with it. So I got HCN, and it's going to go back and forth between H plus and CN minus. So this is what we're having right now. So we're going back to the idea. The NaOH has canceled out. Whatever's left, the NaOH is gone. It's been used up. The sodium is the spectator ion. So now we're going back and forth on this. Now we're back to this. Okay, like our first problem that we had, except now we have less acid because the base has been canceling it out. Now we have to sit there and look at the initial concentration of this. Okay, so hey, what's going to be our initial concentration? Well, our initial concentration is going to be 0.00042 moles over 0.58 liters. Okay? Now, why the 0.58 liters? Because you had 50 milliliters of HCN, our acid, and then you added 8 milliliters of the base, the NaOH, in there. So we have to take that into account. Okay? Now, what else do we have here? Well, we also have here H, it's 0. You know, for the sake of argument, there's nothing, it's really tiny. But on the other hand, we have to look at the CN because it also has had a leftover. We know that it's 0.0008 over 0.58 liters, because that would be how much is left, that it's been taken over. So now we have got our first part of the ice table done. Now we got to look at the change. Well, the change in this case, this is going to decrease. It's going to be a negative X, right? The H is going to be a positive X. Remember, that's where we're going to get our pH. And then here it's also going to be a positive X. Okay? So, with that, ladies and gentlemen, let's look at our equilibrium. Well, what does our equilibrium say? Well, our equilibrium says 0.00042 over 0.58 minus X. All right? That's going to be our concentration here. Okay, we have a plus X, and then we have a 0.0008 over 0.58 liters. okay, with a plus X added onto it. So those are our three concentrations at equilibrium. Everything is now settled. The rate going back and forth is the same. Remember, that's the idea behind equilibrium. Woo! Okay, now that we've come to this point, we can sit there and say, you know what, for the sake of argument, let's assume X to be really, really small. Like the popularity of some presidential candidates out there. Because this is an election year. God bless America. Okay? So now that we have that, we can assume it to be small. Let's go ahead and let's do a little bit of work here. Hang on, I think, let me double check here for my work. You know what, I made a mistake. This is not, it's not 00042, it's 042. Okay, got it. So I gotta make sure I did this right. All right, yeah. Sorry, I wanted to make sure I got that correct. So that's 0.0042. I do apologize for that. Okay, so moving on here as I flip. So let's go ahead and we got 0.0724 and X and 0.0138. Now our Ka in this case, we got that from the top, is equal to 6.2 times 10 to the minus 10th. That's going to equal 0.0138 X over 0.0724. Okay, we're working our way through. We're going to multiply both sides here by 0.0724. So what we're going to get, ladies and gentlemen, we're going to get 4.49 times 10 to the minus 11th is equal to 0.0138 X. Now, solving for X here, okay, X is equal to 3.253 times 10 to the minus 9. Yes. Okay, so that's our X. That's our concentration of our hydrogen ions. That's what we needed to find out here. We needed to find our concentration of hydrogen ions because what's the pH? It's the negative log of the hydrogen concentration. That's what we're looking for. That's why we're going through all this. Okay, now, ladies and gentlemen, we can finally put this one in the bag here. We know that the pH is equal to the negative log of our concentration of our H+. Well, what is our H+? It's the 3.253 times 10 to the minus 9th. So the pH is equal to the negative log of 3.253 times 10 to the minus 9th. Remember, that's the concentration of our hydrogen ions there. And thus, ladies and gentlemen, our pH is equal to 8.49. Woo! Yeah, that's something. That is absolutely something. Okay, guys, so moving on. Okay, and I'm trying to take into account my time here. Oh, okay, sorry. Thought my stopwatch was being faithful. Okay, I'm probably going to have to do this in 2 videos. That's fine. So, titration of a weak acid, again with a strong base. We're working with the same acid, 50 milliliters of 1 molar HCN titrated with 0.1 molar of NaOH. Here's our Ka. Now the question comes down to is, we're halfway through the titration, what's the pH? Well, here's the question. What do you mean by halfway through the titration? The idea, when you say halfway through the titration, it's the number of moles of H+ that's given off by our HCN is going to equal half the number of moles of OH- that's given off by our sodium hydroxide. That is what they are referring to when we talk about halfway through the titration. That's exactly what they are referring to. Okay. So what do we know? Well, we need to figure out how many moles of H are we going to get to begin with. And there's a real easy way to do this. We know that 0.05 liters multiplied by 0.1 molar concentration gives us 0.005 moles of H plus. Okay? So that's what we've got going for us. Now, hey, what's half of 0.005 except 0.0025 moles of OH minus? Well, now that we have that, we know, and you're saying, where did I get this? Well, remember that molarity is equal to moles over liters. Always remember that formula. Very important when we're working with the concentration here. So let's look at it in this way. So 0.05 liters times 0.1 molar, we get 0.005 moles of H plus. This is using our molarity formula. We now know we need half of this because we need half the moles of the OH in there. So now the question comes down to is, okay, we're now trying to find our 0.01 molar NaOH times X milliliters is going to equal 0.0025 molar. Okay? So we can figure out that our volume basically is going to be 0.25. Okay, let me double check here. I'm missing, no, got everything. Boom, 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 boom. I'm just double checking my stuff here. Okay. So we need about 25 milliliters of this stuff, or 0.025 liters. Okay. So there is something that we need to know though. There's a couple of things. So that's how much, base that we're going to need. Now here's the thing. At the halfway mark, there's a couple of things. One, the hydrogen ions, the concentration is going to equal our Ka. And our pH is equal to pKa. So we can do this. We can go ahead and we can turn around and say negative log of 6.2 times 10 to the minus 10 is equal to 9.21. So thus our pH is equal to 9.21. So we are at the halfway point. The pH has gone up a little bit as a result for this. I do have one more part, but that's going to take a little bit longer than what I have here. Okay, so I'm going to continue this with part 2. All right, I'm hoping this helps you guys out.